All right, so number one should be pretty quick. We should get through that one really quick because we did these yesterday. The pieces of the sides that are where that parallel segment is making contact with, where they're intersecting. So those pieces are proportional. So I need a scale. My scale looks like here, like it could be 20 over 11. If you want to use 11 over 20, that's fine. But now if they want to know JG, which is this part over here, does JG correspond to the 11 or the 20? 11. The 11 because it's on the same side, yeah. So JG would have to line up with the 11. What corresponds to JG on the other side? 30, yeah. So cross multiply. With 11 times 30. 20 times JG is equal to 330 divided by 20. That's going to give me a decimal. But as long as it doesn't repeat, if this is a measurement, just keep the decimal. Patty's my decimal girl, thank you. Well, which one did you say? Oh, you said it was what? 16.5? I am right after the one with the part. We're not doing the trapezoid. Yeah, the one from yesterday, right after the one that we were at. Okay. And Mickey, I just noticed that you put a star by the next one. Any questions on this one? Yeah, I put a star by it also. So I was looking through the ones that we have left, and I saw this one. This one kind of snuck by me, and it's like, geez, hold on a second. You know, I have nothing. The geometry teachers have like they share materials, and it could be the mistakes might be on my part. I actually emailed them to see if it was my mistake or just something that was overlooked. But I don't have anything on what's called angle bisector theorem, which is actually that's what would be applied into. As of right now, you know nothing about angle bisector theorem. So since I caught that, just in case, I have no indication that that's going to be on the test next week. But just to be safe, let's just do a few of them. And then so what I did is I'm going to do number 2, but then I went and added a couple extra that are not in your packet. Because I realized this after those were printed, but that's fine. You can write these in afterwards. Now, the good news is, even though this has not too much to do with what we've been doing, because, see, look, because of those 2 arcs, what does that mean about those 2 angles? They're congruent. The two smaller little angles here. No. What? No. This angle is the same as that one. But the fact is, if it has 1 arc each, they're congruent. If they would have drawn, 2 arcs, then 2 arcs, they're congruent. They don't have to be like perfectly like lined up with each other. The fact is 1 arc, right? Where it's different though is those are not similar triangles. The 2 smaller triangles that are created are not similar, but there is proportionality there. So that's something called angle bisector theorem. If you have a triangle where you draw an angle bisector, we went over that before, right? When we went over the special segments of a triangle. Yeah. What were the 4 special segments of a triangle? No, special segments. He's talking about like. No, not midpoint. What are the 4 special segments of a triangle? Obviously, I just told you one of them. Patty? Well, okay, we explained mid-segment on the same lesson, but there was really 4 that didn't count as one of them. Let Hattie go. No, you don't remember them? Altitude was one of them. Okay, so I'll let you continue altitude. And I gave you angle bisector. There's 2 more. Plane. Over here. Somebody wants either from them? Give me 2 already. Altitude and angle bisector. Mickey. Close now. The midpoint. Alternate. Damn, segments. Special segments. That's horrible.
Median.
Was it me? Oh, median. All right, that's 3. Oh, hey, he gets first shot. He gets first shot at Steven it. Fourth one. No. Anybody else want to steal it? Here's the fourth one. Yeah. So median angle bisector altitude. One more.
Well, I know it's it's like something either.
It does start with a P.
I know it is. Parallel. No parallel. Just said that's not it. I said perpendicular. Perpendicular bisectors. Yeah.
What was it? Perpendicular bisector. Perpendicular bisector. So, because I like him the best.
Everybody else.
And actually, he answered more than anybody else. But actually, whoever took the last one would have taken it anyways. But I also like him better though. That's not fair. Anyway, so when you draw an angle bisector in a triangle, the how can I say this? We learned that angle bisectors start at an angle and go away from it. Once it reaches the opposite side, those two measurements are proportional, as are the measurements from the two sides that the angle's coming out of. So, like if I wanted to set up a proportion, what would my scale here be? What would my scale be? I just circled what's proportional to each other. I circled to you what corresponds. Circle them for you. Like I circled for you what to put in the fractions. You definitely don't want to use anything with an X as a scale. A scale is something that you want to know. Yeah. Now I also want to give a disclaimer that there are some times where you can still solve for an unknown without a scale. So it's not like you have to know both of them. But yes, in most cases, right. So this is my scale. And if I set up my first fraction this way, what would the second fraction be? 12.5 is on top. 7.5 is on the bottom. Come over here. What would be on top? X plus 5 over x minus 5. So even though those are similar triangles, you still have a proportion. I don't have any evidence to say that this is going to be on the test, but just in case. 12.5 times x minus 5 is equal to 7.5 times x plus 5. So 12.5x minus 62.5. Addy, 62.5, 12.5 times 5. He gave no. How do you never use up? 12.5 times negative 5. Okay, equals 7.5x, 37.5. All right, x is together, minus 7.5x, minus 7.5x, plus 62.5, plus 62.5. X is on the right, cancel. 62.5 is cancel. I've lined up my like terms. 5x is equal to 100. X is 20. And that's all. I'm watching. They do one of the sides. So they want to know SR and ST. So I got my X. SR was that plus 5, which is 25. ST was the 20 minus 5. So now these coming up are not going to be on your notes, but just write them in somewhere on the side, draw a picture of it. Just try your best to sketch it. This is being recorded, so you can also go back and watch this online if you don't get it all written down. You see the angle bisector coming out. So what's proportional? As you follow the angle bisector, once it reaches the opposite side, those two measurements are going to be proportional. So are the two that are across from each other. Give me a scale. That's perfectly fine. You could have also said 25 over 15. By the way, what is this called that we're using? This property that we're using? No. The property that we're using right now. Close. Oh, look at that. Teeth are going to fall out. Good. If he did have 25 over 15, that would have worked also. But if he put the 15 on top, what? Let's call this x. What lines up with the 15? What's on the same side as the 15? The x. What's on the same side as the 25? 10. 25x is equal to 15 times 10. So 25x is equal to 150. How many quarters are there in $1.50?
5. 6.
For these, we'll just stop when we find x. If you're drawing the picture, let me get these out. Look at the next one. There's a couple ways you can do this. There's a real algebra way that you're gonna feel uncomfortable, you're gonna feel yucky with, and then there's and then there's more of like kind of an arithmetic way to do this. Okay, so notice how here we're looking for this entire side, right? Well, that's not proportional to anything. So the more arithmetic-y way that's not too algebra-y is to call that x. And then now once you find x, though, then you have to at the end add 2. That would be one way of doing it. Okay. The other way to do it, is if I wanted to call this x already, this is the more algebraic way. So if I want to just go straight to my answer and call this x, well, that's not proportional to anything, but this is. So what could I define that as? If the entire side is x, a chunk of it is 2, what would I call what's left over? 4. Very good. Very good. That would just be x minus 2. And then now if I do it that way, once I solve for x, I'm all set. Let's see what corresponds. Wyatt, give me a scale for this one. Thanks, Wyatt. And if I write it, you could also write it as 4 over 2, but if I write it as 2 over 4, what would go on top of the 2? X minus 2, good. What will go on the bottom of the 4? Just, this 2 here. Cross multiply, like you do in the hood. 4. I know everything.
Alright, Wyatt. You guys chill out with that. That was bad.
So x is 3. But just remember that in this scenario, we defined x as that entire side, so we're done. If you would have only defined x as this little piece, what do you think you would have gotten? Instead of a 3, what would you have gotten? 7. Oh, sorry. Too much arc on the J. Any questions? We'll do one more page of these, just in case. When's the test? Next Thursday, right after trick-or-treating. So on this next one here, we have an angle bisector. But here, instead of giving you each piece of the opposite side, they give you the entire 5. So what would then this little piece? Because I don't care about the 5. I care. Yeah, this would be 3 because 5 minus 2 is 3. What can I use as my scale? Well, believe it or not, you actually could use 6 and 3, but like, let's just keep it uniform because I don't want to confuse people. Yeah, 2 and 3. Because let's just keep it to the opposite side and then the lateral sides. I understand that, but I'm gonna confuse people. That's not what I've used on the past 3. What he's saying is to use this, which actually could be used, but what we've been using on all the ones before are the lateral sides, the sides that are across from each other, and then the pieces that are on the side that it touches, on the opposite side. So if I do 2 and 3, what's on the same side as the 2? 2x minus 12, what's on the same side as the 3? The 6. Good. Cross multiply. 3 times 2x minus 12. Distribute 6x minus 36 is equal to 12 plus 36. X is 8. Yay. Cam, you alright, man? Practice this morning too? Oh, man. He looks like a superhero right now. He's got like his mask on. Or a ninja, that's true. All right, last one. This will be the last one with angle bisector theorem. Leilani, give me a scale. You actually could use 15 over 9. I'm not going to say that you can't, but if we want uniformity, if we want to treat it the way we've treated all of them, we've been comparing the lateral sides in one fraction and the pieces on the other. So for the record, yes, if you were to use 15 over 9, then you'd have to use 2x minus 2 over 6. That would work. I promise you it would work. But let's just keep things uniform because I don't want to confuse anybody. Well, so based on the way we've been doing them, what would be a yeah, let's do 6 over 9 because there we know both of them. But if I do 6 over 9, what has to go on top? What's on the same side as the 6? 2x minus 2. Mickey, yes, got that? Okay. Cross multiply, 9 times 2x minus 2, 6 times 15, 18x minus 18 is equal to 90. Plus 18 plus 18, 18x is equal to 108 divided by 18. Is it 6? You cold in here? Okay. So those were kind of just in case if I went too fast. Go back home, open the YouTube video, hit pause, write it down, play a little bit, hit pause, write it down. And now we get back to what were on the original notes. How would I verify here that those two lines were parallel? Notice how we're not looking for any segment. But if these lines were to be parallel, what would have to be true?
And C, B.
9 over 12 would have to be equal to 13.5 over. We talked about this yesterday. If you want to just divide and compare the decimals, that's fine. If you want to reduce, even though that would be ugly here with a decimal, you could do that. Or you could just cross multiply. 9 times 18 would have to be equal to 12 times 13.5. 9 times 18 is 162 in my head. And then 162. So are those two lines parallel?
Yes.
Find the length of the segment. Which one we want? PN. All right. Somebody that has a Cam, give me the scale here. If you can't see it, you just look at the papers. Okay, 2 over 3 will work. Ricky, give me the second fraction. If you can't pick 2 over 3. He already picked 2 over 3, so now you give me the second fraction. Okay, you can say 5 over x. I'm going to just use 5 over pn instead of the x, but yeah. So when I cross multiply, 2 times pn is equal to 3 times 5 equals 5. 2 times pn is equal to 15 divided by 2. Pn. We don't like decimals, but at least we don't have to round here. So 7.5. What? And then the last one was this proof. No? You recognize that diagram? Yeah, I do. Isn't that on the first page of the notes? First page, right? First page of the notes doesn't have, or was it the notes before? Was it this notes or the packet before? Right, yeah. Well, do you have the one from before? Do you have the one from that was just similarity? The one that before parallel proportionality theorem? Yeah. Because I remember pointing out what this is gonna end up being. So watch, they tell you what, I haven't even read what the top says, they tell you what's given, and all they want to know here is step 2, right? They want to know why HGK, which is down here, is congruent to IHJ, and then they want to know why IKG, double arc, is the same as IHJ. And I know I mentioned that once we showed, remember when I was telling you about overlapping triangles, and then it's probably good to separate them? And we were talking about the shortcuts for triangles and why these are like, why are those two triangles, it's not what you're being asked, but why are those two triangles similar? What shortcut, if I were to separate those two triangles, angle. So that's why the triangles are similar, but why are the angles congruent? Because I remember mentioning that when corresponding. They correspond. If these are the parallel lines, maybe this is flashback Fridays. And then this is the transversal. Look at the red arcs. Aren't they both on the top right? If instead of that being the transversal, if this were the transversal that connects the two parallel lines, look at the blue double arcs. Aren't they both on the top left? Therefore, they correspond. Corresponding angles. Any questions there? All right, so we got 10 minutes left. Let's at least start the trapezoid packet. Let's see if we how much we can get through, and then maybe on Monday we can at least get one Kahoot in. Bazit, do you love Kahoot? When it's what? Social studies. Oh, social studies? Okay, then it's like Jeopardy. Yeah, math Kahoots are probably not as fun as that. But I might not do it this time around because it's like I lost a day with having to give you the midterm for the second day and stuff. But like the next time we have an entire day for a Kahoot, I've seen a lot of people that like will do math Kahoots, but then they'll like splice in pop culture questions. I might toy around with doing that. Yeah. So maybe throw in some questions about 1D, and then Mohammed will take over.
No, I'm used to it now. I can't. I can only sit with a blank page. I'm not sure. You just always have
These teachers.
No, it's fun. It's almost really sarcastic.
Worse than me?
Oh yeah.
All right, so this is a lesson that's been tossed around for like 3 or 4 weeks. Originally, this was supposed to be part of the parallelogram unit and also would have been part of the parallelogram test, but scheduling issues, it got delayed. Then it was supposed to be last week, but then with the midterm thing, it got delayed. So now we're finally here. Trapezoids and kites. Both of these are types of quadrilaterals. Okay. Some of the properties that pertain to these might be either similar or in some cases even the same as with parallelograms, but the thing we need to establish is that these are not parallelograms. What were the 4 types of parallelograms? Somebody raise your hand.
Oh, yeah. Oh,
Go ahead, Josh.
oh, snap. I'm a square right.
More obvious than you might think. Mickey for the steal? No. Why? What are the 4 types of parallelograms? He said rhombus, square, rectangle.
Breathe.
Yeah. If you have a problem with Swedish fish, maybe.
No.
So let's talk about some of the differences, because Josh, actually no, trapezoids are not parallelograms. Kites are not parallelograms. It's completely separate realm. The only thing that they have in common is that they're both quadrilaterals. They both have 4 sides. So a trapezoid, unlike a parallelogram has 2 sets of opposite parallel sides, a trapezoid has only 1. The set of parallel sides are called the bases. The other 2 sides are called the legs. Now, what some people tend to think is that the legs have to be congruent. That is not true. In order to be a trapezoid, the only requirement is that you have 1 set of parallel sides, and those sides are called the bases. Now, if that's a conditional statement, if the legs happen to be congruent, then that's a special type of trapezoid called an isosceles trapezoid. That's if the legs are congruent. So that's what I just said. Look, if both pairs if we have an isosceles triangle, not only are the legs congruent, but now both sets of base angles. So I guess I should talk about that. If there's 4 sides, how many angles does a trapezoid have? 4. 4, right? So the angles that ride along the same base, those are called the base angles. So like, not here. Let's give them numbers. Okay. So 3 and 4 are the base angles of the bottom base. 1 and 2 are the base angles of the top base, right? If we have an isosceles triangle, the base angles are congruent. Not only are the legs congruent, but if this was indeed isosceles, then 1 and 2 would be the same, and 3 and 4 would be the same. That's what this theorem here says. The next one, this is a biggie too here because we don't seem to be confused. If our trapezoid is isosceles, the diagonals are congruent. What other type of quadrilateral that we've learned about has congruent diagonals? Right? Becky? Actually, no, wait, get back. There you go. I thought you said rectangle the first time. Rectangle and square. Didn't somebody over there say rectangle and square first? Oh, okay, that was you. And then you were trying to steal it from Bazit.
I have my hand.
Yeah, but it wasn't a rhombus, it was a rectangle. Yeah, well, I was looking at all the people with the hand raised first. None of them were saying the right thing. Okay, and then the next thing, and it's funny because a trapezoid is a quadrilateral, but you could even argue that a trapezoid has more similarities with a triangle. Because if you take a triangle and you were like to slice it, what do you got?
Half the triangle. A trapezoid.
That's a trapezoid, yeah. Like, look, you already saw one similarity with a triangle. That word isosceles, when's the last time you saw it? Triangle, yeah, triangle. Here's another one. A mid-segment. When's the last time you saw a mid-segment?
Yes.
Well, actually, we saw it. You saw it today, yeah, with a triangle. You saw it with triangles, but now trapezoids can also have mid-segments. This is where I'll close it off. On a triangle, what do we know about a mid-segment? It's half the third side. With a trapezoid, it's half the sum of the bases. You have to add the two bases and then divide by 2. Here they have it as times 1/2, but you can also divide by 2. We'll pick it up on Monday, and if we can finish early, we'll get at least one Kahoot in.